Hi everyone, I'm Aniket. So we are having Metropolis algorithm for Ising model. It is an computational technique used to study the behavior of magnetic spins on a lattice at different temperature. By performing simulation at various temperatures and analyzing the result, you can observe how system evolves over time and undergoes phase transition. So we have Ising model. So it is in used to study the behavior of magnetic spins as we discussed in a lattice. It is often used to stimulate the phase transition in magnetic material. We have nearest neighbor interaction because of two reasons. Computational efficiency and nearest neighbor interaction is strong enough that our next nearest neighbor interaction. This is how we have calculated the interaction energy between the two spins. So J is coupling constant. It represents the strength of the interaction between the two. Sigma I, sigma J, these are the spins. It can have two values, plus one and minus one. This is how the 2D lattice are we have and the spins that plays in a lattice. This is a magnetization. This is the way we have defined it. M into N, these are the number of spins in an 2D lattice, this 2D lattice. So there is one more critical thing, which is phase transition. It is a transition from disorder state to order state. In another word, it's a transition from paramagnetic state to ferromagnetic state. The temperature at which it occurs, it called critical temperature. If the temperature that we are working on, if it is greater than critical temperature, then thermal fluctuation dominates. Whereas temperature that we are working on, it is less than critical temperature, then spin try to align in a way that it minimizes the energy. Okay, so this is the part of the code. So in which we first define the energy. This is the way we had defined it. Then there is a loop where the things are repeatedly going on. There is something called acceptance probability. If the randomly generated number, if it is less than that acceptance probability, then the change will get accepted, otherwise it will get rejected, and the energy for that it will be the same as it was before if it gets rejected. And the time that we will consider in the next slide for qpi and the sequential code also is for this part of code only. This is the main code. Okay, main computational code where the computation is happening. So these are the results for QPy. It's an GPU accelerated library. It is very compatible with NumPy. It it has significant speed up only for high computational tasks. So as you can see, for very less lattice size, the NumPy work very effective than QPy. Whereas if we increase the number of spins or the lattice size, then the performance for QPy it is getting effectively better than the NumPy, and the speed up over NumPy is getting increased up to 150 also, as we can see. These are the graph for code, for the time taken by the code with QPy and without QPy. So red part is for time taken by QPy and black part is for time taken by sequential code. So as we see that for QPy, the time taken by the code is going somehow constant up to this point, and for sequential code, normal sequential code, it is going somehow exponential. The maximum speed up that we have gotten for 24,000 lattice size, it was 150, approx 150. So you may get the speed up greater than 150, 200 or 300 for large number of lattice sites than 24,000. So the same thing is reflected in the speed up also. At a certain point is going linear. So we may get the speed up of factor greater than 150 after 24,000 lattice site. Yeah.
Welcome all, I'm Nikhil and I'll cover the CUDA part for the Ising model project for the course IDC 606. All the runs have been done on the GPU, which is NVIDIA's RTX A5000. The computing capability version for the GPU was 8.6. Now, for each run, the thread per block was 1024. That is the maximum number of threads which can be used for a block. As the code is a 2D code, so we are using 32 threads in Y direction and 32 in X direction. That is a total of 1024. The flow of the program is as follows. The first config is set. This config is then sent to the GPU's global memory, and then energy and magnetization is calculated at each point by the thread. All this locally calculated energy and magnetization is then added into a shared variable which is stored in the shared memory of the block, and all these shared variables will be then atomically added at the end of the function. Now, as you can see, for every time when the thread has to calculate energy and magnetization, it has to access the config which is stored in the GPU's global memory. This part can be speed up by implementing stencil, and here I'll show how the stencil implementation was done. This is almost same as it was done in the forward difference method. So here I'm declaring the shared variables. First one is for the energy, second one is for the magnetization, and third one is for the stencil config. This is where the stencil config will be stored. Here I'm defining the indices which will be used to access the stencil. Here, this is exactly same. Only the difference is to write the overall coordinate in terms of x and y. You have to add total number of element in a row, have a jump of 1 in y direction. This is because we are accessing a 2D type array in a 1D fashion. The next will be for the regular point that is the points which are in the middle of the stencil. This is directly a straightforward copy, and this was also done in the same way in the forward difference method. For the hello, for the x-axis, it is again the same as it was done in the forward difference method. For the y direction, you have to take care of how many element you need to add or subtract when you have to change the y index by 1. And here for the config, it is n by 2, n plus 2, and for the stencil config, it is block dim plus 2. And here I have highlighted it in a green box. Now let's see how the energy and magnetization was calculated. This is done in a straightforward way as it was done in the Python code. Only here we are running this for every point. For the temp magnetization, it is directly a copy, and all this will be added for each block. It will be locally added. So here the local addition is done, and all this local variable which is stored in each block will be then atomically added. And En is the energy and magnetization, and mag is the magnetization. So here the atomic adding is done. Also, a function was needed to flip the spin of the config which is stored in the GPU global memory, and this can be seen here. This is the function. Also, the array enm which is required to store the value of energy and magnetization at each iteration of the loop has to be defined dynamically because for the very large value of loops, static allocation won't work because the compiler won't declare such long arrays in a static way. So that's why the static and the dynamic allocation was done. Now let's see the speed up part. So here is the speed up table for the 5000 by 5000 grid. You see there will be a speed up of around 400. The speed up get increased as we keep on increasing the grid size, and also the speed or the execution time for the Python relative to the C code get slower as we keep on increasing the grid size. This is one of the observations. Also, this comparison time has been done only for the part where the energy was calculated in Python and the CUDA C. But if we also have included the part where the config was set, then the speed up will be at least three values more as shown here. And this was another of the observation which I made. And thank you. That's all what I wanted to tell. Thank you.
Hello everyone, myself Rupam, and I am here to discuss on metropolisizing model which we will solve by multi-threading. So multi-threading meaning we have a large data set and we will divide it into threads, and that those threads will calculate on the data set, and they will actually calculate simultaneously and they will give us result at a time. That is how we are getting speed up from the normal sequential code. So this is our energy function. So in this energy function we are calculating the nearest neighbor, s1 dot s2. This is along the row and this is along the column. We have a 2D lattice actually. So this is the target function. In this target function we have a global variable, and by this init and end variable we are actually dividing the array by indexing into these threads, and they are calculating each thread, they are calculating energy by this statement. And this thread log actually meaning that only one thread will access this global variable at a time, and then we will get our result from in this sum variable. So this is the for loop, two for loops actually. These two for loops are for to start the threading and to stop the threading process. This is the magnetization function. In this magnetization function it is np.sum and so on. The differentiation, we are taking this to calculate specific heat, that means d by dt. This is the correlation function. Correlation function, that is average of si dot sj. So for that we have to calculate first nearest neighbor, second nearest neighbor, third nearest neighbor for all the atom, and then we have to take the average. To calculate this as a function of distance we will do this for loop. So this is all about the code, multi-threading code. And let's see this is giving us the actual result or not. We are comparing our result with the sequential normal sequential code. So from the sequential code we are getting this energy versus step graph at low temperature and as well as high temperature. So at low temperature the energy is decreasing with the steps and magnetization is increasing. This is at low temperature, it is going to 1 and energy is going to very low. But in case of high temperature it is opposite to the low temperature actually. And from the same nature of the graph we are getting from our multi-threading code, that means our code is valid. So this is the speed up with the array size and number of threads. We can see that with the increase of threads the speed up is decreasing, and at number of threads, when the number of threads is 4, we are getting speed up of around 4.5. When we will take 6 it is not very low, but it is nearly that 4.5 4.2. And when we, let's say number of threads is 4 and this array size we are increasing the grid size actually 10 to the power 2, 10 to the power 3, 10 to the power 4, and then we can see that the speed up is increasing. First of all, the speed up is 0.03. That means that multi-threading code is slower than the sequential. But when we are at 10 to the power 5, 10 to the power 6 it is increasing, and at 5 into 10 to the power 6 it is 4.3, around 4.3. So now if we see that previous table is of with the array size how the speed up is changing. Now in this table this indicate that with the step size how the speed up is going. So with the increasing step size, speed up also increases. When the step size is 10 to the power 5, when array size is 10 to the power 3 cross 10 to the power 3 number of threads 4, then we are getting this speed up of 6.3. And this is the graphs. This along the y-axis it is time, along the x-axis it is log of steps. So that means here it is 1 2 3 4 5, that means 10 to the power 1, 10 to the power 2, 10 to the power 3, and after crossing this 10 to the power 3 steps it is actually giving us the speed up, because this is the time for sequential and this is for multi-threading. Similarly for the array size the speed up is like this. When it is 5 into 10 to the power 6 we are getting a large speed up actually. From the speed up graph we can see that for the step size it is on around 6.3 when the steps is 10 to the power 5, and in case of array size it is 4.3 and so on. That depends on the array size and also the number of steps, that means iterations. From the multi-threading code we are getting these results. So this is the initial state, this spin orientations actually. This spin orientation has been generated from the random number generator, and then in two different temperature, one is at 2.5, one is at 1.5. We ran the code and then we got two graphs. It is this graph, the spins are not aligned along the same direction, that means the system is disordered, and in this case these spins are aligned, that means it is ordered state. So that from this picture we can conclude that between this 2.5 and 1.5 we have the critical temperature. Below of it the system is ordered and above of it is disordered. So to see how what is the critical temperature, we have to see the energy versus temperature graph, and then we can conclude something. So this is our energy versus temperature, this is magnetization versus temperature, and this is specific heat. From this graph we can see that at low temperature energy is very low, it is around minus 20,000. So as we increase the temperature above 1.5, it is the energy is changing very fast up to 2.6, and then the change is becoming low. Similarly for magnet, and the energy is increases. Okay, in case of magnetization, it is initially it is nearly 1, that means the system is ordered, all the spins are aligned along same direction. And similarly for after 1.5 and up to 2.5, this magnetization changing rapidly. So that means critical temperature lies between these two temperature, as we said before. So this is the specific heat. Specific heat means this is the derivative of energy with the temperature, d by dt. So this specific heat has a peak at around 2.35. So that means the critical temperature is around 2.3, and that is why above 2.3, this is 2.5, we were getting this disordered state, and below critical temperature 2.35 it is ordered. Then we have calculated this correlation with the distance. So here we have varied this temperature and calculate the correlation average of SISG with the distance. Distance means this is the indices. Actually this 1 2 3 4 5 6, these are the neighbors. That means 1 means this is the first nearest neighbor of a reference pin, 2 means second nearest neighbor, 3 means third nearest neighbor, and so on. As we increase the temperature, at low temperature this correlation is constant with the distance as the system is ordered, and when we increase the temperature this correlation is decaying with the distance, and as we go beyond the critical temperature then this is falling very fast. If we zoom this area then we will get this graph actually. So as we increase the temperature above critical temperature, let's say this is 2.4 2.5, this is 2.4 2.5, this is the above critical temperature, then this correlation function is actually becoming exponential and it is decaying exponentially. So from this we can conclude that this correlation length, that means the length up to which the spins are correlated with our reference spin approximately, so that correlation length also decreases with temperature, and at critical temperature it has a peak which indicates the phase transition from one phase to another. That means at low temperature it has the ordered state, that means below critical temperature, and above critical temperature it has the disordered state. So that is why when at t equals to tc, and the correlation length has a peak, and that indicates the phase transition. So that's it for today. Thank you.